Good evening, people. How are you guys doing? All right, my name is Archit Sharma. I'm a PhD student at Stanford, and I'm very, very excited to talk about post-training, generally speaking, for large language models. And I hope you guys are ready to learn some stuff, because this has been one of the last few years in machine learning have been very, very exciting with the advent of large language models, ChatGPT, and everything to that extent. And hopefully, after today's lecture, you will be more comfortable understanding how we go from pre-trained models to models like ChatGPT. And we'll take a whole journey through prompting, instruction fine-tuning, and DPO and RLHF. So let's get started. All right. So something that has been very fundamental to our entire field is this idea of scaling laws. And models are increasingly becoming larger and larger, and they're expending more and more compute. So this is a graph of models starting all the way back in 1950s to somewhere around, this is an outdated graph. So like this shows up to 10 to the power 24 flops, or floating point operations that go into pre-training these models. But the number is well above 10 to the power 26 now. But you can see the graph and the way it's trending. And more compute requires more and more data because you need to train on something meaningful. And this is roughly the trend on the amount of language tokens that are going into the language models in pre-training. And again, this plot is outdated. Does anybody want to guess, like we're in 2024, 2022 we were at 1.4 trillion tokens, or words roughly speaking, in language model pre-training. Does anyone want to guess like where we are in 2024? That's a pretty good guess, yeah. So we're close to 15 trillion tokens. Recent Llama 3 models were roughly trained on 15 trillion tokens. So yeah, just for a second, appreciate that these are a lot of words. This is not, yeah, I don't think anybody of us listens to like trillions of tokens in our lifetime. So this is where we are right now. And I hope you guys were here for the pre-training lectures. Cool. So what do we do? So broadly speaking, we are really just learning to predict text tokens or language tokens. But what do we learn in the process of pre-training? Why are people spending so much money, so much compute? Because these compute and tokens take dollars to do, and we're on the order of spending hundreds of millions of dollars on these runs. So why are we doing this? And this is basically a recall from whatever you've probably learned till now. But we're learning things like, we're learning knowledge. Stanford University is located in Santa Clara, California, or wherever you want to say. You're learning syntax. You're learning semantics of the sentences. These are things that you would expect to learn when you're training on language data. Broadly, you're probably learning a lot about different languages as well. So depending on your text data distribution, you're learning a lot of things. But the models we interact with are very intelligent. So where is that coming from? Just simply learning about very factual things. And it's a very simple loss function we're optimizing. And where is that intelligence coming from? And this perhaps is the interesting bit. Recently, people have started accumulating evidence for that. When you optimize the next token prediction losses, you're not just learning about syntax. You're not just learning knowledge. But you're starting to form models of agents, beliefs, and actions as well. So how do we know this? Again, a lot of this is speculative evidence, but it's maybe to form an understanding that the losses we're optimizing are not just about the data, fitting the data, but you start learning something maybe more meaningful as well. For example, in this specific case, we change the last sentence, and the prediction of the text, or the next text that is predicted, changes as well. So here it starts with Pat watches a demonstration of a bowling ball and the leaf being dropped at the same time. Pat, who is a physicist, predicts that the bowling ball and the leaf will land at the same rate. We all know gravity, the way it works. But when you change the last sentence to Pat, who has never seen this demonstration before, Pat predicts that bowling ball will fall to the ground first. Maybe somebody who's never seen this experiment before might intuitively believe that. Correct? So the language model was able to predict this. So how do you predict this? You have to have some notion of understanding of how humans work to even be able to predict this. And that's maybe something that is not obvious when you're simply optimizing to predict the text. Similarly, like, I mean, these kind of examples we're going to run through some examples to like sort of communicate that when you're pre-training these models, you're learning much more than just language tokens and so on. You're also learning about math. Like you're able to understand what a graph of a circle means and what the center is and how to like understand equations. Probably my favorite example, something I use pretty much every day, is you're learning how to write code. So I don't know how many of you have interacted with Copilot before, but if you have, like, you probably know, like, if you write down a few comments, write down a function template, it will automatically complete code for you. So again, it's not perfect, but it has to have some deeper understanding of what your intent is for something like that to emerge. And similarly, we have examples from medicine as well. I don't know about you guys, but like whenever I have some issue, I probably go to ChatGPT or Claude or something to that effect and ask them a diagnosis for those things as well. I don't recommend that. Please don't take medical advice from me, but yeah. So broadly, like the way we're seeing language models at this point is that like they're sort of emerging as this general purpose multitask assistants. And it's very strange, right? Like, I mean, we started off with text token prediction and we're reaching the stage where we can like sort of rely on them to do many, many different things. So how are we getting there? And I'm sure you all are aware of like what these models are, so yeah. So today's lecture is largely going to be about how do we go from something Stanford University is located, this very simple pre-training task, a very simple procedure. Well, it's more complicated, but in abstract terms, it's not very complicated, to like something as powerful as ChatGPT. Cool. So I recommend you guys stopping me, asking me a lot of questions, because there's a lot of fun examples and a lot of fun techniques. So like I want you guys to like learn everything about here. So the overall plan is we're going to talk about zero-shot and few-shot in context learning. Next, we're going to follow up with instruction fine-tuning. And then we're going to talk about optimizing for preferences. And this is where roughly things are right now in the industry. And then we're going to talk about what's next, what the limitations are, and how do we move from here. Cool. So we're going to start off with zero-shot and few-shot in context learning. Broadly, we're going to take an example of GPT, or the generative pre-trained transformer. And this is a whole series of models that started off in roughly 2018, and like up to 2020, they were building GPT, GPT-2, GPT-3. So we're going to start off with this example. And yes, so it's a decoder-only model that is trained on roughly 4.6 gigabytes of text, and it has 12 layers of transformers there, and it's trained with the next token prediction loss. And the first model obviously was not extremely good, but it started showing that like, hey, like this technique for pre-training can be very effective for general purpose tasks. And we're going to see some examples. For example, like, I mean, here it's able to do the task for attainment and, yeah, and GPT-1 itself was not very strong as a model. So like, but they took the same recipe and like, I mean, tried to like increase the model size. So they went from 117 million parameters to about 1.5 billion parameters. And we're now scaling up the data alongside as well. So we went from 4 gigabytes of data to approximately 40 gigabytes of data. And pre-training is a whole different like melting pot of techniques, and there's a lot that goes into it. But like roughly, for example, here, they filter data by the number of upvotes on the Reddit data. And yeah, so this is roughly where we are. And I think one of the things that started emerging with GPT-2 is zero-shot learning. And what do we mean by zero-shot learning? Conventionally in the field, like when we pre-train models, there was the idea that you take a few examples, you update the model, and then you are able to adapt to a specific task. But as you pre-train on more and more data and more tasks, you sort of start seeing this phenomena where they're able to do the task basically zero-shot. They're shown no examples of how to do the task, and you can start thinking of, oh, how you can do it summarization, you can follow some instructions, you can do maybe a little bit of math as well. So this is where the idea of zero-shot learning started to emerge. Yeah, so how do we do zero-shot learning or task-specific learning from these pre-trained models? Really, the idea is like we have to be creative here. We know that these are text prediction models. If you put in a text, they will complete whatever follows. So if we can sort of coerce these models into completing the task we care about, maybe it's question answering, we can start getting them to solve tasks here. So for example, if you want to ask questions about Tom Brady, you sort of set it up. You sort of put information about Tom Brady, and then you put a question that you wanted to answer, and then it will auto-complete in some sense. So this is one early perspective on these models. These are very advanced autocomplete models. And similarly, if you want to figure out like which answer is true or which is not, something that is very useful to measure is log probabilities. So, for example, we want to figure out what is the word it referring to here in this sentence. The cat couldn't fit into the hat because it was too big. What we can do is we can take the sentence, replace it with either the cat or either the hat, and then you can measure the probability of which one does the model think is higher, and you can sort of get the idea of what the reference here is. So none of this is like in the training data. It's simply learning to predict text. But you can start seeing how like we can leverage these models to do other tasks as well besides prediction. So this is just more evidence about like how GPT-2, no task-specific fine-tuning, no task-specific training. It simply is learning to predict text, and it establishes the state of the art on many, many different tasks, simply by scaling up the model parameters and scaling up the amount of data it's trained on. So this is a fun example. So if you want to do summarization for data, or like you have a news article that you want to summarize, so how do you get a zero-shot model to do it? This answer is you put the document into the context, and you simply put TLDR in front of it. Now, like, I mean, if most of the data on the internet, whenever you see TLDR, you'll naturally summarize it. So yeah, you can get zero-shot performance and summarization here as well. And again, this is not trained to do summarization in any specific way, and it's still doing really well, simply because of its pre-training data. So yeah, I think GPT-2 TLDR is somewhere there, and like some of the very task-specific trained models are and I think you will see the trend with, again, if you were Alec Radford or somebody, like, I mean, you see like these cool things emerging, your next step would obviously be, I'm going to scale this up a little more. I'm going to make an even bigger model. I'm going to train it on even more data, and we'll see how things go, right? So that's how we got GPT-3. We went from 1.5 billion parameters to 175 billion parameters. We are well over like 40 gigabytes of data to 600 gigabytes of data. Of course, like now we're in like terabytes of data, and text is a very compressed representation, so like terabytes of data is a lot. And you know, we talked about zero-shot learning. The cool thing that emerged in GPT-3 is like, go ahead.
So typically, like TLDR is used before the passage, right?
No, you typically put the passage. If you've like interacted with Reddit or something like that, typically somebody will write an entire post and then end with TLDR. Here's a summary of the thing. Too long, didn't read. Or if you've used...
Opposite. Like TLDR comes first.
Oh yeah, there are situations where it also comes first, but one reason is that these are like decoder-only models, so like these are causal attention models, so they typically need to see the context before.
Yeah, that's what I understand. I'm just curious, like from my experience, if TLDR comes first, then how is it able to map it back to the passage before?
Yeah, okay. There's probably a lot of data where the TLDR comes first, but there's probably a lot of data where TLDR comes after as well. Cool. So we saw zero-shot learning emerging in GPT-2. Few-shot learning maybe seems slightly easier, but like this is where things started getting really funny, is that like you're starting to beat state of the art simply by just putting examples in context. So yeah, what does few-shot learning mean here? What are we talking about? As I mentioned, like the typical idea here is that like you want to solve translation. So you would put some examples of translation into context. And you know, this is a correction task here, or maybe you're interested in translation. And no gradient updates, no learning in any conventional sense whatsoever. You put a few examples in, and that's it. Like, I mean, you know how to solve the task. Isn't that like crazy? Like, you guys did the assignment on translation, right? So, but this is what the modern NLP looks like. So, yeah. You put in some examples and you have the entire system. And this is where things got really interesting, is that all these task-specific models that were created to like be really, really good at translation or really good at summarization, you can just put let's look at this graph. So we start with the zero-shot performance of this in a similar fashion that I described earlier, and you start somewhere there. You put one example in of translation from English to French, you get to somewhere like already at a fine-tuned level. Few examples in, you're already starting to like be close to the state-of-the-art models.
Wait, but in that graph, the state-of-the-art is really high, isn't it? The fine-tuned state-of-the-art?
Fine-tuned the BERT++ here, I think, is like the what I'm referring to. Fine-tuned state-of-the-art, like where it's just trained exclusively on a lot of translation data, might be like slightly better, yes. And I think that's the relevant comparison here is just the in-context learning starts to emerge at scale. So, and this is, I think, like the key point is that some of this is contested, just to be very upfront, but like there's this idea of emergence of this property as you train on more compute and more scale. There's more recent research which suggests that if we plot the x-axis correctly, it feels less emergent. But the general idea is as you increase the number of parameters and increase the number of compute that is going into the models, the ability to just go from a few examples to really strong performance is very compelling. Cool. And yeah, I think as I explained earlier, the general idea is that this is very different from the conventional idea of fine-tuning that we typically go for. Instead of like iterating over examples, putting it into context and doing gradient updates, we are actually just going for few-shot prompting. We're going to put in few examples, and that's going to give us the system. Go ahead.
Just to clarify, you're pre-pending
Yes. I mean, the exact details roughly can depend on the prompt template that you use, but typically you would just put examples. So like C order and put these examples, and then whatever your task is, you can just let the model complete from there because it can infer the task based on the examples you've given. Any other questions? Cool. So yeah, like I mean, we have gotten from zero-shot prompting, and like we're seeing that few-shot prompting is becoming really competitive with good models. But there's still limitations to this. Like I mean, you cannot solve every task that you see here, and particularly like things that involve like richer multi-step reasoning is something that actually can be pretty challenging. And just to be fair, humans struggle at these tasks as well. So things like addition and so on, like these are probably like still hard to do, like when you keep increasing the number of digits. But one thing that you have to start being creative with, I alluded to this earlier, is that you can get these models to do the task if you're creative in how you prompt the model. And this is what we're going to see next. So this technique called chain of thought prompting emerged here. And the idea that we have explored thus far is that we put in examples of the kind of tasks we want to do, and we expect the model to zero-shot learn what the task is and go from there. The idea is that like instead of just showing what the task is, you show them examples where they reason through the task. So they're not just learning to do the task, but also learning how the reasoning is working. So in this example, initially we started with like we have to solve a simple math problem, and we are just shown exactly the answer directly. Instead of doing that, and if you do that directly, you'll observe that the model gets the answer wrong. Instead of that, what if you show model how to reason about the task, show it a chain of thought, and include that in the prompt as well? And then you ask it a new question. The idea is that now the model is not just going to output an answer, it's going to reason about the task, and it's going to do actually a lot better. And this has been shown to be very effective. Chain of thought is also, as you can see, like I mean, it's again something that improves a lot with model scale. It's not just, but what you can probably start seeing is like it's nearly better than supervised best models here. So PAM models roughly were about 40 billion parameters. And simply with this chain of thought kind of a skill, you're already like beating state of the art. Cool. So I showed you examples of chain of thought reasoning up to this point where you go through a reasoning chain, but you can be even slightly smarter than that. You might not even need to show them any examples. You just need to trick them into thinking about what to do next. This idea emerged in this paper called where we were, let's think step by step, where instead of even showing an example, you just start your answer with let's think step by step. And that's it. Like, I mean, the model will start reasoning about the answer itself instead of just like auto-completing to an answer. And you get something like this. So maybe you don't even need to show any examples. Like, you can probably induce the reasoning behavior through zero-shot behavior as well. And again, what the final numbers look like is like compared to zero-shot performance that we got from essentially auto-completing, this zero-shot chain of thought substantially improves the performance. So you go from like 17.7 to 78.7. It's still worse than still putting like examples of reasoning and multi-shot, few-shot chain of thought as well. But you can see like how much it improves the performance simply by asking it to let's think by step by step. And maybe this is like a lesson that interacting with these models is like, when you interact with these models, you might not get the exact desired behavior from these models up front, but often like these models are capable of doing the behavior that you might want. And often you have to think about how to induce that behavior such that, and the right way to think perhaps is like, what is the pre-training data, what is some data on the internet it might have seen which induces a similar behavior to the kind I want? And you probably want to like think about that and then induce these kinds of behaviors from those models. And yeah, like, I mean, we've hand designed some of these prompts. You can also like get an LLM to design these prompts as well. There's like recursive self-improving ideas here that happen, and you can bump up the performance a little bit more. Cool, so what we have seen so far is that as models get stronger and stronger, you can start forcing them to do your tasks zero-shot or with few-shot examples, and you can trick them into thinking what task you want them to solve. But the downside is that there's only so much you can fit into context. This might not be very true anymore. Models are becoming increasingly larger context, but it's still somewhat unsatisfactory to think you have to trick the model into doing your task rather than like it just doing the task you wanted to do. And potentially, like, I mean, going forward, like, you probably still want to fine-tune these models for more and more complex tasks. And that's where we're gonna go forward in this. Next section we're gonna cover is instruction fine-tuning. And the general idea we have right now is that, as we talked about, pre-training is not about assisting users. It is about predicting the next token. Now, you can trick it into assisting users and following the instruction you want it to, but in general, that's not what we retrained it for. And this is an example where if you ask GPT-3, pretty strong model, to explain like moon landing to a 6-year-old in a few sentences, and it will follow up with more questions about what a 6-year-old might want. This is not what you wanted the model to do, right? So the general term that people use these days is that they are not aligned with user intent. And the next sections that we're going to cover are going to talk about how to align it with the user intent so that they don't have to trick the model into whatever we want it to do. And this is the kind of like desired completion we want at the end of instruction tuning. And yeah, how do we get from those pre-trained models to models which can respond to user intent? Again, I hope this was covered somewhere in the class, the general idea of pre-training and fine-tuning. But what you have probably seen thus far is that you pre-train on a lot of different language tasks, on data, but then you fine-tune on your specific task. So you're taking the same decoder-only models, and you're fine-tuning to some task with very little amount of data. The thing that is going to be different now is not that we're no longer fine-tuning on a little amount of data, we're going to fine-tune on many, many different tasks, and we're going to just try to put them into a single usable UX for users. And this is where fine-tuning or instruction fine-tuning comes in. Cool. So again, the recipe is not very, very complicated here. We're going to collect a lot of examples of instruction and output pairs, and the instructions are going to range over several tasks, different forms. There's going to be question answering, there's going to be summarization, translation, code, reasoning, and so on. And we're going to collect a lot of examples related to all those tasks. And the idea is like, I mean, we'll train on instruction and output pairs exactly with them. And then we're going to evaluate on some unseen tasks as well. So this is a general paradigm of instruction fine-tuning. And again, it's the same idea which we explored in pre-training, is that data plus scale is really important. And these days, like, I mean, you start off with like one task, you're now extending it over thousands and thousands of tasks with like 3 million plus examples. And this is generally like a broad range of tasks that you might see in instruction fine-tuning data sets. And yeah, you might even think of like, why are we calling it fine-tuning anymore? Like, it's almost starting to look like pre-training. But yeah, these are just terms. So you can decide whatever you're comfortable with. So yeah, we get this like huge instruction data set, we fine-tune our model. The next question is like, how do we evaluate these data sets? Now, I think you guys will see another lecture on evaluation, so I don't want to like dive too deep into this. But generally, evaluation of these language models is an extremely tricky topic. There's a lot of biases that you need to deal with, and a lot of this will be covered. But some more recent progress on this is like we are starting to curate these like really large benchmarks, like MMLU, where the models are tested on a broad range of diverse knowledge. And this is just one example, and these are the topics that you will see. And just to give some intuition of what the examples in these evaluations look like, under astronomy, you might be asked what is true for type 1a supernova. Or you might be asked some questions about biology. And there's a huge host of tasks for this. And you can typically these are multi-choice questions, and you can ask the model to answer the question. If they're instruction fine-tuned already, hopefully they can simply answer the question, but you can also chain of thought prompt these questions or few shot prompt these questions too. And recently, there's been a huge amount of progress on this benchmark. What people have observed is more and more pre-training on more and more data and larger models is simply just climbing up these. The number on this, so 90% is often seen as a benchmark number that these models wanted to cross, because it's roughly human level knowledge or understanding. And recently, the Gemini models purportedly crossed this number. So yeah, go ahead.
Isn't this the entire sort of thing all over again, right? Imagine at some point you're okay, maybe my methods are too fine-tuned implicitly on the imaginary biases, and isn't something like that happening here as well?
Yes, I think this is a tricky topic because a lot of the models often, there's this idea about whether your test sets are leaking into your training data set, and are huge concerns about that. It's a perfectly valid question to ask. How do we even evaluate? This is why evaluation is actually very tricky. But one general thing to be careful about is at some point, it doesn't matter what your trained test is if the models are generally useful. If the models are doing useful stuff, does it matter if you train on everything you care about and it does well on it, does it matter? So yeah. Again, we still need better ways to evaluate the models and to understand what methods are doing and if they're improving the model or not. But at some point, those boundaries start to be less important. Cool. So massive progress on this benchmark, starting with GPT-2, and we're roughly at 90%, which to the point where these benchmarks are starting to become unclear if improvements on these are actually meaningful or not. In fact, most of the times when the models are wrong, you might often find that the question itself was unclear or ambiguous. So all evaluation benchmarks have a certain limited utility to them. So yeah, I'm gonna go over another evaluation example of how this recipe changes things. So T5 models were instruction fine-tuned on a huge number of tasks. And another trend to emerge, which I think will be the theme across this lecture, is that as your models become larger, as they're trained on more data, they become more and more responsive to your task information as well. So what you will observe here is as the number of parameters increase, we have T5 small, flan T5 small, and we go up to 11 billion parameters where we have T5 XXL. You'll see that the improvement actually improves, going from a pre-trained to an instruction model. The instruction model is all the more better at following instructions. So the difference is plus 6.1 and it goes to plus 26.6 as the models become larger. So this is another very encouraging trend that you probably should train on a lot of data with a lot of compute. And pre-training just keeps on giving. So yeah, I I hope you guys get a chance to like play with a lot of these models. I think you already hopefully are. But yeah, before instruction fine-tuning, something when you're asked a question related to disambiguation QA, you get something like this, and it doesn't actually follow the let's think by step-by-step instruction very clearly. But after instruction fine-tuning, it is able to answer the question here. And yeah, like more recently, people have been like researching into like what the instruction tuning datasets should look like. There's a huge plethora of instruction tuning datasets now available. Like this is just a representative diagram, and there's a huge open source community developing around these as well. Some high-level lessons that we have learned from this is, one lesson that I think might be interesting is that we can actually use really large, strong models to generate some of the instruction tuning data to train some of our smaller models. So take your favorite model right now, GPT-4, maybe Claude or whatever, and you can get it to answer some questions and generate instruction output pairs for training your open source or smaller model. And that actually is a very successful recipe. So instead of getting a human to collect all the instruction output pairs or getting humans to generate the answers, you can get bigger models to generate the answers as well. So that's number one thing that like has recently emerged. Another thing that is being emerged or is like being discussed is how much data do we need? I talked about millions of examples, but like people have often found that if you have really high quality example, you can get away with 1,000 examples as well. So this is the paper less is more for alignment, and this is still an active area of research on how like data scaling and instruction tuning affects the final model performance. And yeah, crowdsourcing these models can be effective as well. So there are very cool benchmarks that are emerging, like Open Assistant. Yeah, a lot of activity in the field, and hopefully like a lot more progress as we go on. Yes?
A question sort of in the spirit of this Lima paper, doesn't like code or like, I don't know, like math word problems have this desired structure? So like, shouldn't we just like be training code models and be doing like some English stuff and then just be like, okay, this is the best reasoning we can get at some point, right? Because like code has the structure where like you're going sort of step by step and you're sort of thinking in some way in like a sort of breaking down a higher concept into smaller. So you can consider like code that has like very high value tokens. So maybe like just doing.
So I think there's, again, pre-training is a whole dark art that I am not completely familiar with, but code actually ends up being really useful in pre-training mixtures. And people do like upweight code data quite a lot. Similarly, like, I mean, but it depends upon what the users are going to use the models for, right? Some people might use it for code, some people might use it for reasoning, but that's not the only task we care about. As you might see later on in the next step, we'll discuss this as well, is that people often use these models for creative tasks. They wanted to write a story. They wanted to generate a movie script or so on. And I don't know if like necessarily training on reasoning only tasks would help with that. So go ahead.
Yeah, would you expect like there exists like some data distribution which is like high value for creative tasks?
Yes, like I mean, it seems like a lot of people write about stories and everything on the internet all the time, like which is not code. And sometimes like there's this idea of hallucinations as well in this like field, but you can often think like, hey, like creativity might be a byproduct of hallucinations as well. So I don't know what exact data would like lead to like more creative models, but generally like there's a lot of data or a lot of stories that are written on the internet which allows the model to be creative. Yeah, but I don't know if I have a specific answer to the question. Cool, so we discussed instruction fine-tuning. Very simple and very straightforward. There's like no complicated algorithms here, just collect a lot of data and then you can start leveraging the performance at scale as well. Like as models become better, these models also become more easily specifiable and they become more responsive to tasks as well. We're going to discuss some limitations, and I think this is like really important to understand why we are going to optimize for human preferences. Cool. So we talked a bit about this, like instruction fine-tuning is necessarily contingent on humans labeling the data. Now, humans, it's expensive to collect this data, especially as the questions become more and more complex. You want to answer questions about which may be at physics PhD level or things to that effect. these things become increasingly expensive to collect. So yeah, this is maybe like perhaps obvious, like collecting data. Pre-training does not require any specific data. You scrape data off the web. But for instruction fine-tuning, you probably need to recruit some people to write down answer to your instructions. So this can become very expensive very quickly. But there's more limitations to this as well. And we were just discussing this, like there are open-ended tasks related to creativity that don't really have like an exact correct answer to begin with. So how do you generate the right answer to this kind of a question? And yeah, like language modeling inherently like penalizes all token level mistakes equally. This is what supervised fine-tuning does as well, but often like not all mistakes are the same. So this is an example where you're trying to do this prediction task. Avatar is a fantasy TV show. And perhaps you can see like, I mean, calling it an adventure TV show is perhaps okay, but calling it a musical may be like a much worse mistake. But both these mistakes are penalized equally. And I think one general aspect which is like more becoming increasingly relevant is that the humans that you might ask might not generate the right or the highest quality answer. Your models are becoming increasingly competitive, and you want, in some sense, you're going to be limited by how high quality the answer humans can generate. But often I find that the models are generating better and better answers. So do we really want to keep relying on humans to write down the answers, or do we want to like somehow go over that? So these are the three problems we have talked about with instruction fine-tuning. And we made a lot of progress with this, but this is not how we got ChatGPT. And one high-level problem here is that even when we are instruction fine-tuning, there is still a huge mismatch between the end goal is to optimize for human preferences, generate an output that a human might like. And we're still doing prediction kind of tasks where we're predicting the next token, but now in a more curated data set. So there's still a bit of a mismatch going on here, and it's not exactly what we want to do. Hopefully, like, I mean, I'm going to take a second here to pause because this is important to understand the next section. And if there's any questions, feel free to ask.
So is this step still taken as a first step, or did we discard this?
That's a good question. So I think this is still one of the more important steps that you take before taking the next step. But people are trying to like remove the step altogether and jump directly to the next step. So there's work emerging on that. But yeah, this is still a very important step before we do the next step. Go ahead.
Is programming 2 also present in pre-training? And if so, how do you avoid that, or just by having a lot of data?
Yeah, that's a great question. There's one major difference on pre-training. Pre-training covers a lot more text. So just for context, like, I mean, as we talked about, pre-training is roughly 15 trillion tokens, whereas like supervised instruction fine-tuning might be somewhere on the order of millions to billions of tokens. So it's like few orders of magnitude lower. Typically, you'd only see one answer for a specific instruction, but during pre-training, you'll see multiple texts and multiple completions for a same kind of a prompt. Now that's good, because when you see multiple answers or completions during pre-training, you sort of start to weigh different answers. You start to put probability mass on different kind of answers or completions. But instruction fine-tuning might force you to put weight on only one answer. Does that, okay. But generally, yeah, like, I mean, this is a problem with both the stages. You're right. Anything else? Cool. So as this whole thing alludes to, we're going to start to attempt to satisfy human preferences directly. We're no longer going to like try to like get humans to generate some data and try to do some kind of a token level prediction loss. We're going to try to optimize for human preferences directly, and that is the general field of RLHF, and that's the final step in typically getting a model like ChatGPT. So we talked about how collecting demonstration is expensive, and there's still a broad mismatch between the LM objective and human preferences. And now we're going to try and optimize for human preferences directly. So what does optimizing for human preferences even mean? To like concretely establish that, let's go through like a specific example in mind, which is summarization. we want to train a model to be better at summarization. And we want to satisfy human preferences. So let's imagine that the human is able to prescribe a reward for a specific summary. Let's just pretend there is a reward function you and I can assign. Say like reward, this is +1, this is -1, or something to that effect. Okay. So in this specific case, we have this input X, which is about an earthquake in San Francisco. So this is a news article that we want to summarize. And let's pretend that we get these rewards and we want to optimize this. So we get one summary Y1, which gives us an earthquake hit and so on, and we assign a reward of 8.0, and another summary which gives us a reward of 1.2. Generally speaking, like the objective that we want to set up is something of the following form, where we want to take our language model P theta, which generates a completion Y given an input X, and we want to maximize the reward of RXY, where X is the input and Y is the output summary in this specific task. And maybe like just to like really concretely point out something here, this is different from everything that we have done in one very specific way. We are sampling from the model itself. In the bottom term, if you see, like we're using Y from P theta. Everything we've seen so far, the data is sampled from some other source, either during pre-training, either in supervised fine-tuning, and we're maximizing the log likelihood of those tokens. But now we're explicitly sampling from our model and optimizing potentially a non-differentiable objective. Cool. So broadly, the RLHF pipeline looks something like this. And first step is still instruction tuning, something we have seen up until now, where we take our pre-trained model, we instruction tune on a large collection of tasks, and we get something which starts responding to our desired intent or not. But there are two more steps after this which are typically followed in creating something like InstructGPT. The first step is estimating some kind of a reward model, something which tells us, given an instruction, how much would a human like this answer or how much would a human hate this answer. So we looked at something like this earlier, but I didn't talk about how do we even get something like that. That's the second step. And then we take this reward model and we optimize it through the optimization that I suggested earlier. So the maximizing the expected reward under your language model. And we're going to go over a lot over in the second and third steps. So the first question we want to answer is, how do we even get like a reward model about what humans are going to like? Like, this is a very ill-defined problem, generally speaking. So there's two problems here that we're going to address. First is that human in the loop is expensive. So let's say like if I ask a model to like generate an answer, and then I get a human to label with some kind of a score, I'm doing this over millions of completions. That is not very scalable. I don't want to sit around and label millions of examples. So this is very easy. Like, we're in a machine learning class. So what are we going to do? So what we're going to do is we're going to train something which predicts what a human would like or what a human might not like. And this is roughly, this is essentially a machine learning problem where we take these reward scores and we try to train a reward model to predict, given an input and output, what the reward scores would look like. Simple machine learning regression style problem. You might have seen this earlier. Cool. Now there's a bigger problem here. And sorry, go ahead.
For step one, so do we use like, I don't know, like just embeddings with a specifier, or do we use a real language model to do that?
That's a good question. Generally, like what we do is like, we still typically need reward models where they need to be able to understand the text really well. So like bigger models, and like they're typically initialized from the language model that you pre-trained as well. So you typically start with the pre-trained language model and do some kind of a prediction that we'll talk about, and they'll give you a score.
How do you, if you're doing that, how do you separate X and Y? Like, how does the language model know which part to which?
It doesn't need to. It can put the X and Y, like it only sees X and Y as an input. So it doesn't need to typically see it separated. It's just going to predict a score at the end.
Okay.
Yeah. The X and Y is more for notational convenience here, because for us, X and Y are different. X is a question user asked, and Y is something the model generated.
But you shove the whole thing into it.
You shove the whole thing into one. Yes. Cool. Now this is the bigger problem here, and human judgments are very noisy. We've talked about we want to assign a score to a completion, this is something that's like extremely non-trivial to do. So if I give you a summary like this, what score are you going to assign on a scale of 10? If you ask me on different days, I'll give a different answer, first of all. But across humans itself, this number is not calibrated in any meaningful way. So you could assign a number of 4.1, 6.6, and different humans would just simply assign different scores. And there are ways to address this. You can like calibrate humans, you can give them a specific rubric, you can like talk to them, but it's a very complicated process, and like still like there's a lot of room for judgment, which is not typically very nice for training a model like this. If your labels can vary a lot, it's just hard to predict. So the way this is addressed is that instead of trying to predict the reward label directly, you actually want to set up a problem in a slightly different way. What is something much easier for humans to do is give them 2 answers, or maybe many answers, and ask them which one is better. So this is where the idea of asking humans to rank answers comes in. So if I give you a whole news article and ask you which summary is better, you might be able to give me a ranking that, oh, this second summary is the worst, but the first one is better, and the third one is somewhere in the middle between those two. So you get like a ranking which gives you preference over summaries. And hopefully, like, I mean, you can see like the idea that is important here is that even when we have some kind of a consistent utility function, even when it's much easier to compare to something and know that which is better than this rather than ascribing it an arbitrary number on a scale. And that's why the signal from something like this is a lot better. Now, how do we get we talked about we get this kind of a preference data, and now we need some kind of a reward score out of this. And we shove in our input, we shove in a summary as well, and we still need to get a score out of this, but it's not clearly obvious to me, how do we take this data and convert it into that kind of score? In comes our pretty good friends named Bradley Terry. And essentially, there's a lot of study in in economics and psychology, which basically tries to model how humans make decisions. In specific case, this Bradley Terry model essentially says that a probability that a human chooses answer y1 over y2 is based on the difference between the rewards that humans assign internally, and then you take a sigmoid around it. So if you've looked at binary classification before, the logit is simply the difference between the reward of some y1 minus y2, or the difference between the winning completion and the losing completion. Is everybody with me till this point? So the idea is that if you have a data set where given y1 and y2, where y1 is a winning completion and we have a winning completion yw and a losing completion yl, the winning completion should score higher than the losing completion. Go ahead.
Sorry, what is J? Is that a log prop or
Sorry, what?
What is the type of J? This number here that we're getting as the expectation, is it a log prop or what is it?
It's an expected log prop, so it will be a scalar at the end. Sigmoid is, so you're taking let's say you have a reward model which gives a score R1 to YW and R2 to YL. You subtract that number, you get another number. You put it into sigmoid and you get a probability, because sigmoid will convert a logit into probability. And then you take a logarithm of that. And you take the expectation of everything and you get this final number which tells you how good your reward model is doing on the entire data set.
So a good model of humans should behave like this.
A good model of humans would score very low here. So it would generally assign a higher reward to the winning completion and generally assign a lower reward to the losing completion. Cool. The math is just beginning, so hold on to your seats. Cool, so now let's see where we are. We have a pre-trained model, P, PT, Y given X, and we got this fancy reward model which tells us that, hey, we have a model of humans and it can tell us which answer they like and which answer they not like. Now to do RLHF, generally, we've discussed what this will look like. We will copy our pre-trained model or our instruction-tuned model, and we'll optimize the parameters for those models. And I suggested that the objective that we want to optimize is the expected reward when we sample completions from p theta. And we're going to optimize our learned reward model instead of like the true reward model, which humans would have typically assigned. Do you guys see any problem with this? Is there something that's wrong here, or like that might go wrong if we do something along these lines? Go for it.
The model will collapse.
It might collapse, yes. But generally, at least from my intuition, like if you're ever doing something and you're optimizing some learned metric, I'd be very careful, because typically our loss functions are very clearly defined, but here my reward model is learned. When it's learned, it means it will have errors. Yes. So it's going to be trained on some distribution. It will generalize as well, but it will have errors. And when you're optimizing against a learned model, it will tend to hack the reward model. So it might the reward model might erroneously assign a really high score to a really bad completion. If your policy learns, or if your language model learns to do that, it will completely hack that and start generating those gibberish completions. So just as a general machine learning tip as well, if you're optimizing a learned metric, be careful about what you're optimizing and make sure that it's actually reliable. And this is obviously not desirable. Like, I mean, if you start optimizing this objective, you're going to converge to gibberish language models very, very quickly. So typically what people do is that you want to add some kind of a penalty that like avoids it drifting too far from its initialization. And why do we want to do that? Like, if it cannot drift too far from its initialization, we know the initialization of the model is a decent language model. And we know it is not necessarily satisfying this reward model too much. And we also know that like the reward model is trained on a distribution of completions where the initial model is. So typically when we talk about training this reward model, we have trained it on certain completions which are sampled from this initial distribution. So we know the reward model will be somewhat reliable in that distribution. So we're just going to simply add a penalty which tells us that you should not drift too far away from the initial distribution. And just to go over this, we want to maximize the objective where we have RM phi, which is our learned reward model, but we're going to add this term beta log ratio, and the ratio is the model we're optimizing p theta, and our initial model pt. And what this says is that if we assign a much higher probability to certain completion as compared to our pre-trained model, you're going to add an increasingly large penalty to it. And simply you're paying a price for drifting too far from initial distribution. If you guys have taken like machine learning, the expectation of this quantity is exactly the Kullback-Leibler divergence or KL divergence between p theta and ppt. So you're penalizing drifting between two distributions. Go for it.
Shouldn't you also do this, like add a penalty in the previous version where you had the fine-tuning? Or is this only relevant for the RLHF?
That's a good question. So I think people do add some kinds of regularization in fine-tuning. It's nearly not as critical when you're doing this. With RL, like the incentive is to exploit this reward model as much as possible. And we'll see examples where like the learned reward model predicts like it's doing really well, but the true reward models are completely garbage. So it's much more important in this optimization. Cool. So now, this course does not assume background on reinforcement learning, so we're not going to go into reinforcement learning, but I just want to give a very high-level intuition about how this works. And reinforcement learning is not typically just used for language models. It's been applied to several domains of interest: game-playing agents, robotics, developing chip designs, and so on. And the interest between like RL and model LLMs, it's also like dates back to roughly like 2016 as well, but like it's been really successful recently, and especially with the success of RLHF. The general idea is that we're going to use our model that we're optimizing to generate several completions for an instruction. We're going to compute the reward under our learned reward model, and then we're going to simply try and like update our model to increase the probability on the high reward completions. So when we sample a model, we'll see completions of varying quality, and we'll see some good completions, good summaries for our task, some bad summaries for our task, And we'll try to update our log probabilities in a way such that the reward for when you use the updated model, you're typically in the high reward region. Does the high-level summary make sense? Cool. And RLHF is incredibly successful. I think this is a very good example of, this is the same summarization example. And I think the key point here is that the performance improves by increasing the model size for sure. We have seen this in many different examples. What you can actually see is that even very small models can outperform human completions if you train it with RLHF. And this is exactly the result you see here. The reference summaries are human generated, and when you ask humans which ones they prefer, they often prefer the model generated summary over the human generated summary, and this is something you only observe with RLHF, even at small scales. And again, the same scaling phenomena still holds here. Bigger models do become more responsive, but RLHF itself is very impactful here. Cool. The problem with RLHF is that it's just incredibly complex. I gave you a very high-level summary that's there's whole courses on this for a reason. And this image is not for you to understand, it's just completely to intimidate you. You want to fit a value function to something, you have to sample the model a lot. It can be sensitive to a lot of hyperparameters. So there's a lot that goes on here, and yeah, if you start implementing an RLHF pipeline, it can be very hard. And this is the reason why a lot of RLHF was restricted to very, very high compute, high resource places, and it was not very accessible. So what we're going to talk about and cover in this course is something called direct preference optimization, which is a much simpler alternative to RLHF. And hopefully that's much more accessible. But please bear with me, there will be a lot of math on here, but the end goal of the math is to come up with a very simple algorithm. So hopefully it's, and feel free to stop me and ask me questions.
Examples you need from humans, in terms of GPT-4 versus 3, how much does the number of parameters in the base model help with maybe needing to reduce the number of parameters, or reducing the number of examples from humans for RLHFs that work well?
Yeah, that's a really good question. So generally speaking, if you hold the data set size constant and simply increase the model size, it will improve quite a lot.
Sure.
Yeah. But the nice thing is that you can reuse the data and you can keep adding data as you keep scaling models up. So typically nobody tries to reduce the amount of data collection. You just keep increasing both the things. Cool. So we talked about RLHF, and the current pipeline is something we train a reward model on the comparison data that we have seen so far, and we're going to start with our pre-trained or instruction-tuned model and convert it into an RLHF model using the reinforcement learning techniques. Now, the key idea in direct preference optimization is, what if we could just simply write a reward model in terms of our language model itself? Now, to intuitively understand that, what is going on, a language model is assigning probabilities to whatever is the most plausible completion next. But those plausible completions might not be what we intended. But you could restrict the probability simply to the completions that a human might like. And then the log probabilities of your model might represent something which the humans might like, and not just some arbitrary completion on the internet. So there is a direct correspondence between the log probability that a language model assigns and how much a human might like the answer. They can have a direct correspondence in them. And this is not some arbitrary intuition that I'm trying to come up with. We will derive this mathematically. So the general idea with direct preference optimization is going to be, we're going to write down reward model in terms of our language model. And now that we can write our reward model in terms of our language model, we can simply directly fit our reward model to the preference data we have. And we don't need to do the RL step at all. So we start off with some preference data, and we simply fit our reward model to it, which directly optimizes the language parameters. And maybe at a high level, why is this even possible? We did this really cumbersome process with fitting a reward model and optimizing it. But in the whole process, the only external information that was being added to the system was human labels on the preference data. When we optimize a learned reward model, there's no new information being added into the system. So this is why something like this is even possible. For quite a few years, this was not obvious, but like, as you will see, like some of these results like start to make sense. So we're going to derive direct preference optimization. I'll be here after the class as well if you have questions, but I'll hopefully like this is clear. So yes, we discussed that we wanted to solve this expected reward problem where we want to maximize the expected reward, but we subtract this term, which is the beta log ratio, which essentially penalizes the distance between where our current model is and where we started off. So we don't want to drift too far away from where we started. Now, it turns out that this specific problem, instead of doing like an iterative routine, there's actually a closed form solution to this problem. So the closed form solution looks something like this. Again, if you have seen the Boltzmann distribution or something to that effect before, this is basically the same idea. But the idea is this, that we're going to take a pre-trained distribution, PPT, y given x, and we're going to reweight the distribution by the expected reward. So if a completion has a very high reward, it's going to have a higher probability mass. And if it has a lower reward, it's going to have a lower probability mass. And it's determined by the expected reward. And beta is a hyperparameter which essentially governs like what is the trade-off between the reward model and the constraint. And as beta becomes lower and lower, you're going to start paying more and more attention to the reward model. So the probabilities look something like this. And there's this like really annoying term, this zx. And the reason why it exists is that the numerator by itself is not normalized. It's not a probability distribution. So to construct like an actual probability distribution, you have to normalize it, and zx is simply just this normalization.
So real quick, if we write zx out as the sum of all y of
Yes.
pt, okay, great.
Yeah, and that's exactly like, it's sum over all y's for a given instruction. And that's exactly why this is very pesky, is like it's intractable. If I take an instruction and try to sum over every possible completion, and not just like syntactically correct ones, every single possible, we have 50,000 tokens, maybe even more, and the completions can go arbitrarily long. So this space is completely intractable. This quantity is not easy to approximate even. So the main point here is that if you're given a reward model, you can actually, there does exist at least a closed form solution which tells us what the optimal policy will look like, or optimal language model will look like. But if you do a little bit of algebra, just move some terms around, take a logarithm here or there. I promise this is not very complicated. You can actually express the reward model in terms of the language model itself. And I think this term is reasonably intuitive as well. What it says is that a completion y hat has a high reward if the model, my optimal policy, assigns a higher probability to it relative to my initialized model. And this is scaled by beta. So the beta log ratio is what we're looking at here. And the partition function, let's just ignore it for now, but it's intractable. But the beta log ratio is the key part here. Is everyone following along? Awesome, okay. So right now I'm talking about optimal policies, but really like every policy is probably optimal for some kind of a reward, right? Like this is mathematically true as well. So the important bit here is like you can actually express, you take a current policy, take your initialized model, and you can get some kind of a reward model out of it. And this is the exact identity which leads to this. So reward model can be expressed in terms of your language model, barring the log partition term, which we'll see what happens to it. Go for it.
I'm sorry, I don't know how you got there. Like, why is it that we can swap? Because there is a thing that we're trying to optimize, and how did P star turn into PR?
Yeah, for now, like we're not optimizing any reward model.
Okay.
All I'm saying is that if I take my current language model, it probably represents some kind of a reward model implicitly. Because of this relationship, because this holds for every P star and every reward model, what I'm saying is that like if I plug in my current language model, it also represents some kind of a reward model. I'm not saying it's optimal.
Okay. But I want to say, because at the beginning, PRL is PPT.
Yes.
And so we just get that the reward is basically so the
Zero.
log is 0, and so
Yeah.
what do we do?
Initially it's 0, but like we can optimize the parameters.
Okay, okay.
Yeah. Yeah, but that's a good observation that it's basically 0 in the beginning.
But how do we start optimizing if
I'll get to that.
Okay.
Any other questions?
So the idea is that given the language model, you have a reward model such that makes the language model optimal based on it.
Yes. That's the next step, yes. But the key idea is that like my language model, the probabilities already implicitly define a reward model. I think that's really the main point here. And this mathematical relationship is exact. Cool. Now, I'm obviously ignoring the elephant in the room here, which is the partition function. It's not going to magically vanish away. So if this was just the beta log ratio, that would be really nice. I can compute all these quantities. I know how to compute the log probability under my language model. I know how to compute the log probability under my pre-trained model. And I can compute the reward score. And I can optimize this. But I don't know what to do about my log partition function. This is where something fun happens. So recall what the reward modeling objective was. When we started off, with their friends Bradley Terry again. And what we really wanted to optimize was the reward difference between the winning completion and the losing completion. And really, that's all we care about. We don't care about the exact reward itself. What we care about is maximizing the difference between the difference between winning and losing completion. And that's actually really key here, because if you plug in the definition of the RM theta there, what you'll observe is that the partition function actually just cancels out. Now, why does it cancel out? The input is exactly the same. The x is actually exactly the same in the difference. So the partition function zx will just cancel out. It's the same in both the terms. So what you get is that the reward difference between the winning and losing completion is the differences between the beta log ratio for the winning and losing completion. You can plug in the terms, you can work it out, it's fairly simple. So the partition function, which was our which was something we could not address, we could not compute, actually just simply vanished away.
I'm so sorry. Z doesn't appear in the Bradley Terry model.
But it appears here in this equation.
So how does plugging in the Bradley Terry model cancel out Z?
So we're going to take this equation, the last line that you see, and we're going to plug in place of Rm phi. So, and in this, the first loss equation.
Oh, I see. Got it.
Yeah.
Yes.
So the first loss equation is the Bradley-Terry loss model. Cool. So this really is it. The key observation is we could express our reward model in terms of language model, and our problems with the partition function actually go away because we're optimizing the Bradley-Terry model. And what you get is something like this, is that we're going to express the loss function directly in terms of our language model parameters theta. And we're going to be able to directly optimize on our data without doing any RL steps or not. And this is simply a binary classification problem. So we're really just trying to classify whether an answer is good or bad. And that's really what we're doing. Before I go on, people want to absorb this in, feel they're okay with it.
I don't get where the why good and why win and why lose come from. Are they human input or are they derived from the model?
Good question. It's the same data set we started with in RLHF as well, but the way the process works is that you take a set of instructions and get the model to generate some answers, and then you get humans to label which answer they prefer. So they're model generated. Typically, they can be human generated as well, but they're typically model generated, and then you get some preference labels.
Okay.
All you need is a label saying which is a better answer.
What do you lose here? You must be losing some information because of the lack of information about other. You're canceling out so because of the lack of any information about the partition function.
Yeah.
You are bound to lose information about other possible completions which you would have taken into account in standard RLHF, right?
That's a really good question. I don't think I'll be able to completely answer this question in time, but partition function is almost kind of a free variable. So I think the problem here is that the reward model, there's many reward models that satisfy this optimization. So there's a free variable here that you can actually completely remove, and that's what this optimization benefits from. So think of it this way, like if I assign something a reward of +1 and assign something a reward of -1, that's basically the same as saying as it's a reward of +100 and 99. And it will give you the same loss, right? So that scale doesn't, it's shift invariant in a ways.
Isn't that like somehow like not what we want though? Like okay, like if you're actually training a reward model, right? Like 199 is like you should pay much less attention to that as compared to like -1, right?
But
1-0 or something.
What we're assuming is our choice model here is like if a human prefers something over the other, like the probability is governed only by the difference between the rewards. So that's an assumption that every RLHF also makes and like DPO also makes. Now, is that assumption true? Not completely true, but like it holds to a fairly large degree. But that's a good question, yeah. Cool. I'll move on in interest of time. And really, like, I mean, the goal of this plot is to like, we actually get fairly performant models when we optimize things with DPO. So in this plot, I think the main thing that you should look at is PPO, which is the typical RLHF pipeline, and we are evaluating the models for summarization, and we're comparing to human summaries. And what we find is that DPO and PPO sort of do similarly, but you're really not losing much by just doing the DPO procedure instead of RLHF. And that's really compelling because DPO is simply a classification loss instead of like a whole reinforcement learning procedure. So I'm going to quickly summarize. What we have seen thus far is that we want to optimize for human preferences. So, and the way we do this is like, instead of relying on uncalibrated scores, we're getting comparison data and feedback on that. And we use this ranking data to either do something like RLHF, where we first fit a reward model and optimize using reinforcement learning. Or we do something like direct preference optimization, where we simply take the data set and do a classification loss on that. And yeah, like there's trade-offs in these algorithms. Like people, when they have a lot of computational budget, they typically maybe go for RLHF or some routine like that. But if you're really looking to get the bang for your buck, like, I mean, you might want to go for DPO, and that's like probably going to work out of the box. It's still an active area of research. People are still trying to understand how to like best work with these algorithms. So like, I'm not making any strong claims here, but like both of these algorithms are very effective. DPO is just much simpler to work with. Cool. So yeah, like, I mean, let's see, like we went through all this, instruction tuning, RLHF, what do we get? InstructGPT is the first model which sort of followed this pipeline. It defined this pipeline. So we got models which did 30,000 or so tasks. Remember when we were doing like only one task, and now we have scaled it up from 1,000 tasks to like 30,000 different tasks with many, many different examples. So that's like where we are with InstructGPT. And it follows this pipeline that we just described. In this case, they're following a specific RLHF pipeline where we explicitly fit a reward model and then do some kind of a reinforcement learning routine on top of it. And yeah, like the task collected from labelers looks something like this. I'll leave it to your imagination, or you can look at the details. But how we started off with this model was something like completions we see from GPT-3, which, you know, explained the moon landing to a 6-year, and like it is not really following the instructions, but InstructGPT will give you something which is meaningful. So it's inferring what a user wanted from the specific instruction and is converting to a realistic answer that a user might like. And yeah, these are just more examples of what an InstructGPT-like model would do, whereas your base model might not follow the instructions to your desired intentions. And yeah, like we went from InstructGPT to ChatGPT, and it was essentially this pipeline. The key difference here is that it is still doing the instruction tuning, but it is more optimized for dialogue, more optimized for interacting with users. So the core algorithmic techniques that we discussed today are what give us ChatGPT, but you have to be really careful about the kind of data you're training on. And that's really the whole game. But this is the foundation for ChatGPT. And yeah, it follows the same pipeline as well. And you might interact with ChatGPT. I'm sure you all have interacted with it in some form or not, but like this is an example of what a ChatGPT interaction might look like. you want to make it Gen Z. So like, I mean, you can, the idea here is that it's like very good at responding to instructions and intent. This is not something that we could like even few shot in very easily. These are kind of instructions that are hard to come examples for. But like, this is probably not something it trained on either, but it's able to like infer the intent and generalize very, very nicely. And that's something I find personally very remarkable. Cool. And there's been a lot of progress on the open source front as well. So like DPO is much simpler and much more efficient. And essentially all the open source models these days are using DPO. So this is a leaderboard that is maintained by Hugging Face here. So like, I mean, 9 out of 10 models here are trained with DPO. So that's been something that's been enabled the open source community to instruction tune their model better as well. And same is being used in many production models now as well. Mistral is using DPO. Llama 3 use DPO. So these are very, very strong models, which are nearly GPT-4 level, and they're also like starting to use these algorithms as well. And something that's very cool to see is like we went through all this like optimization and like, I mean, math and stuff, but what is really fundamentally changing in the behavior? And I think this is a really good example is that if you simply ask an instruction for and ask for an SFT output from an instruction tuned model, you'll get something like this. But when you RLHF the model, you actually get a lot more details in your answer, and they'll probably organize the answers a little better. And this is something that they maybe humans prefer. That's why it's a property that is emerging in these models. But it's something that's a very clear difference between simply instruction-tuned models and some models which are RLHF'd. So yeah, we discussed like this whole RLHF routine where we are directly modeling the preferences and we are generalizing beyond label data. And we also discussed RL can be very tricky to correctly implement, though the DPO sort of implements this or like avoid some of these issues. And we briefly also touched upon the idea of reward model and reward hacking. And when you're optimizing for learned reward models, you will often see this example is that there's a way for it to just simply crash into the object, keep repetitively crashing the board to get more and more points. That wasn't the goal of this game. So this is a very common example that is shown for reward hacking. If you do not specify rewards well, the models can like learn weird behaviors which are not your desired intent. And this is something a lot of people worry about as well. Part of the reason is reinforcement learning is a very strong optimization algorithm. It's at the heart of AlphaGo, AlphaZero, which like results in superhuman models. So you have to be careful about how you specify things. And the other thing is like even optimizing for human preferences is often not the right thing, because humans do not always like things which are in their best interest. So something that emerges is that they like authoritative and helpful answers, but they often like don't necessarily like truthful answers. So one property that happens is that they'll prefer authoritativeness more than correctness, which is maybe like not something nice. Please go ahead.
Along those lines, I'm curious if maybe like ChatGPT being so like now widely used by the public will maybe change the like how people rate the rewards. Because I at least feel like now when I go to ChatGPT and I type something that gives me 5 like detailed paragraphs of information, sometimes I'm just annoyed by that and that's not what I wanted. But maybe in the original reward function, in the original ratings, people actually preferred that and now they prefer it less.
Yeah. That's a great point because like as these models like integrate more and more into our system, they're going to collect more and more data, and they will like pick up on things, maybe undesirable things as well. As far as I understand, ChatGPT is really cutting down on the verbosity, which is like a huge issue that all of these models are trying to cut down on, and they are dealing with that. Part of the reason why that emerges is that when you collect preference data at scale, people are not necessarily reading the answers. The Turkers might just simply choose the longer answer, and that's a property that actually goes into these models. So, but hopefully like these things will improve over time as they get more feedback. And yeah, hallucinations is not a problem that is going to go away with RL, and we talked a bit about reward hacking as well. Biases from things and so on. But hopefully, like, I mean, what I want to conclude at is like, we started with pre-trained models. We had these things which could predict text, and we got ChatGPT, and hopefully like it's a little more clearer how we go from something like that to ChatGPT. And I'll end here. Thanks.